Thank you. So I'd like to start by thanking the organizers for inviting me, for all of you being here. It's a great privilege and an honor to be here. I'm standing on the shoulders of giants. We just had Jürgen, Paul were both. When I was a kid in '96, I went to this conference for the first time. Paul Werbus was giving a talk about computing backpropagation through time and how no one knew how to do it properly. And so it was refreshing to see him giving that talk, a bit of that talk again today. Today, however, we stand not just on the shoulders of these important giants from the past, but also on the shoulders of everyone that contributes to GitHub, all those developers of frameworks like Theano, like Torch, like TensorFlow, like MXNet, and so on. Because through those frameworks, we now can do backpropagation through time very efficiently. And I think we ought to thank every grad student and every person out there that's done that work for us. Thank you. The inspiration for my work is the following. If children are born, and I should say infants, because this applies to all animals, are born with the ability to do lots of things. A one-year-old person is capable to do things that no machine can do today. It is some psychologists, like Elizabeth Spelke, who will be here at NIPS at the workshops, would argue that we're born with some core knowledge, and this core knowledge is what allows us to learn more efficiently, to quickly learn motor skills, learn to manipulate your parents by the age of 1. They do. They're masters at manipulation. I believe by 1 week they can manipulate parents. I've been through that recently. I will soon show you a video of my manipulator. This, I believe, can be understood as evolution having provided us with systems. This very slow learning process has enabled us to learn fast. And I believe this not only applies at the very large scales of evolution, but it also applies at a more minute scales, the daily basis, the going to college, where you become a better learner of mathematics and so on. So then this begs the question that I think every person who's seriously interested in solving AI will confront at one stage, which is how can a network program another network? How can we implement the ability of learning with other learning modules? How can a network choose the algorithms of other networks? What are programs? What are algorithms? How do they relate to neural networks? And many of these questions have already been answered by many people. I came up with this idea just to find out that there were 1 million papers out there already done before. In fact, the Rumelhart paper with McClelland and Hinton talks about sigma pi units, and it talks about specifically about programmable neural networks. There's no experiments on that, but the idea is there. My inspiration has come actually from Sepp Hochreiter. It has come from Jürgen. They've got some beautiful papers on this, and especially on learning to learn. That's where I drew my inspiration. I later found out that psychologists like Harlow in the 50s, Evans in the 30s, have done incredible work on this. And I strongly recommend you go into the psychology literature. This also, the idea of a network controlling another network is also very much studied in neuroscientists when people think of control and so on. And in general, there's been a huge number of papers on learning to learn, what I call now X by Y, and you can replace X and Y with your favorite words in machine learning. So let's play this. Learning to learn, unsupervised learning by supervised learning. Now, as crazy as that sounds, it's been done. There's a '92 paper by the Benja brothers where they were learning generalized forms of Hebbian learning by gradient descent. Or like I like to call it, getting rid of backpropagation by backpropagation. And of course, you can learn backpropagation rules with reinforcement learning. You can learn reinforcement learning with backpropagation rules and so on. And I actually think now more seriously, this is still worth exploring. We still need to understand all this range. And actually, this is like a creative way to think about the problem. How can we learn Monte Carlo with gradient descent? I think it's achievable. It hasn't been done, but I think this just gives us a recipe for inventing things. Now, in terms of a network, setting the parameters of a network, another network, programming a network, Scott Reed, when he was interning with me, did a very nice project whereby he had an RNN that would choose the program of another RNN. So we would choose a subset of the parameters, shown here in purple, that we would call that the program. And then this RNN would have a common parameter. So here the H's, the usual core of an LSTM or a DNC, is shared among all the RNNs. And RNN will predict which program to call next, what arguments to pass, and will decide whether it should end computation. And it takes as input the caller program, and it looks at the environment. And it manipulates environment. The addition is not happening in the head of the model. The addition is happening in the world, very much like when you do addition, you use a scratch pad and you add. Humans and animals use the environment to do computation and to do their thinking and their storage. Most of you, through your computers right now, are doing that sort of thing. Now, you interact with the environment by calling sub-processes. So your mind goes and does recursion. You use this key value memory as a stack so that you can go recurse down, do something, and eventually when you're done, you can recurse back up. So to illustrate this process, now imagine that NPI module is looking at images of cars, and it's looking at a desired elevation and azimuth, for example, front of view. So it can learn to plan how to move that car by recursing down, performing an action, going back, recursing down until the car is in a front view. So why would we do this? For the following reason. By having more structure in these networks, we're able to solve all these different tasks that I'm showing you here, learn these 20 programs with the same network, and not only the same network, but the same exact parameters. It can learn to generalize to rotate cars. These are cars in the test set. It never saw them in the training set. And it can learn to add, and it can learn to sort, though at present the sorting program seems to be broken. I believe that's the GIF. The other reason for doing this is the way we train these models with traces. So we give it lessons. We don't give it input-output pairs. So this is a bit like cheating. But however, with 8 lessons, we can learn these models. If you go for input-output pairs and try to learn it end-to-end, then you need 1,000 input-output pairs. It is clear to me that input-output pairs is an important part of machine learning. However, imitation learning and apprenticeship learning are equally important. And if you observe animals, you'll also see the importance of this. And it's not clear what puts the most onus on people to produce labels. In this case, I think we should be seriously considering being able to do this apprenticeship learning, because you can learn very quickly, very rapidly. Moreover, by having the structure, the networks generalize much more. Like in this case, for example, learning to sort on the left with sequences of 20 numbers, if you try to then ask the model to sort longer sequences, what happens is that the sequence-to-sequence models collapse very quickly. So I think there were like minimum engineering for maximum impact and minimum generalization. That kind of symbolic generalization is not possible with just plain recurrent neural networks. You need to bring in more structure. So there's 2 types of generalization we need to aim for, symbolic and statistical. We need to be able to deal with images, but we also need to get our networks to be able to eventually output symbols and be able to manipulate symbols. They need to generate Python code, because when you generate Python code, that code will sort numbers of any length up to what the machine allows you. So that's very important. is, again, the world is external. The symbols are in the world, and you manipulate them to be able to do better. This is still a challenge for future research. You can also learn this. This also relates to stack machines. Ed Griffinstead's done a lot of good work in this direction. There's been lots of papers in this area. There's about 20 papers at iClear this year on just neural programming, and in the previous iClear there were also many good programs. Jacob Andreas at Berkeley also has some very nice extensions to reinforcement learning recently, and I should mention the work of Don Song, which is a very nice generalization of these ideas. Now, if you're learning algorithms, it begs the question, can we learn the algorithms that we typically use in deep learning? And the answer is yes. So imagine that you are now doing an update. So you can either do updates by gradients or by something fancier, some function G, like could be Adam or RMS prop. Everyone engineers algorithms at present. And so what I'm going to argue is just stop engineering algorithms just the same way we stop engineering features. Because we can learn the algorithms, and we can do better when we learn the algorithms. We're not there yet at the level at which we can learn features, but I think we should aim to be there. And this, by the way, if you're learning to learn by gradient descent by gradient descent, because most of RL that scales uses gradient descent, this also applies to RL as well as supervised learning. So the computational graph shows you that you're trying to optimize a function, f, that has parameters theta, and your optimizer is a neural network M that will produce the updates for the theta. And then you get a new theta, you evaluate f, you can pass the gradients back into the optimizer, and you keep improving the optimization process. The code, if you want to see the full computational graph, I recommend you look at DeepMind Learning to Learn on GitHub, and the code is there. Now, how does this work? We train this on neural networks, MLPs on MNIST with 20 neurons in the hidden layer. We test what happens when we try to generalize 200 steps to a greater number of units, 40, or to a different number of layers. We compare against Adam, RMS prob, Nesterov's gradient, SGD. In all cases, we really outperform any existing algorithms by a vast margin. So if your job is to learn algorithms for MNIST using sigmoid functions, you are out of a job. You've been automated. If, however, you use ReLUs, you still have a job because we don't seem to be doing well as we try to generalize to other problems. But this is the right way to do things. When you come up with an algorithm, you should do tests, cross-validation tests, to see how good is the algorithm in other tasks. We should apply the same rules to algorithms that we're applying to models at present. Also, I think in this case, ReLU with 20 does poorly on MNIST in general. It's too sparse. So we also try this on CovNets for CIFAR. We see the same behavior. We can actually learn with a subset of the labels and test it with another subset, and it works. We try this with neural art, where you get a style image and an actual content image, and we train the model, and then we change the content, change the style, double the resolution, and run the optimizer and see if it still works, and it does work. And when you're running this optimizer with pre-trained ImageNet models, which is what you're doing here, you effectively are creating a neural network that is about 60,000 layers deep. This is the point that Jürgen was making earlier. And once again, we beat all the existing optimizers on this. It is still a challenge to scale this to very large networks, and the challenge has to do with memory. This is extremely fast. Once you learn that recurrent neural network, M, you can cut it, and you can use it to optimize any function. Josh Saul Dickstein at Brain has shown with his colleagues that you can in fact learn this network in random functions, and then you can use it to train data sets. It's still an open question how well these models will generalize and what are the best training practices. You can also, instead of taking gradients as input, just take function values, or take the steps, the changes in function values, and you can just stop being greedy and going for one single optimum, and you can do global optimization. So you can learn to explore, where you're sort of going for the maximum, but you also need to keep checking all other areas, like the plot shows. Again, we can train this with an RNN. In this case, it's very similar to the work of Sepp Hochreiter and the old days. And this is like black box optimization. So it's the realm of Bayesian optimization. And what we show is if you know the horizon that you're optimizing for, you can do better than things like spearmint that I use for Bayesian optimization. You can test this on, we learn actually with a bunch of functions from a Gaussian process, and then we test it on all these other problems. So we run it on optimizing the Hartman function, which is a very hard function from global optimization. We do well there. We also can optimize some simple control problems, and this optimizer has 0 hyperparameters. Test time is incredibly fast and compared to other solutions, and again, you don't have to tune it. This, of course, relates to the work that Ilya mentioned, learning to learn with RL squared, and also to an excellent paper by Jane Wang that I recommend, as well as a paper by Raya Hatzel and her team on learning to navigate, where they look at a very wide variety of tasks like navigation, as well as standard tasks that are being studied in psychology, as well as bandit problems. Now, the quest for knowledge, and here is the video I promised you, is one of the most important things. That is intrinsic motivation at play. And then she tastes it. The root for knowledge, the word knowledge, and taste is the same. It's the word sapere. Creatures have evolved in an environment to sense. The more you can sense, you have an advantage over other creatures. The better you are. Even plants, in fact, use opsons, molecules as tools to sense light and hence thrive. So I think, and I think that quest for knowledge, for sensing, I think the quest for sensing culminates with the search for knowledge, and that's what we're doing. That's what physicists do when they try to idealize the world, understand the components of the world, the concepts, the mathematical theories, and then when they make predictions that can be verified by experiment. They're also not only designing the solutions, but they're designing the tasks. That's what Jürgen means by power play. You need to come up with tasks yourself, the agent, to be able to do better. And that is one of the biggest challenges we need to face for AI. Very few people are working on that, and I think more people need to think about it seriously. And also the agent should be embedded on environments with physics. And I make this point here, where an agent has to learn the weight of some blocks. This is in Mujok, a physics engine with gravity and contact forces and so on. While you can see the different colors of the block, the agent is blind. The agent sees basically all blocks out of the same color. So the only way you can figure out what the weight is you have to interact. You have to act on the world. If you have a book in your hands and you want to know how many pages it has, don't just look at it. You can get a guess from that, but you're going to have to count. You're going to have to use your hands. Action is fundamental. So just learning from pixels, as many of the environments that have been proposed recently are suggesting, is not enough. In many environments, the agent has to actually be embodied in order to be able to learn. And it has to learn to perform experiments, to improve its knowledge of mass, its knowledge of density, its knowledge that will enable it to solve a wider range of tasks and be able to interact with the environment successfully. There'll be more on this at the DeepRL workshop. Very quickly, a couple more frontiers beyond what Oriel mentioned, and he claimed I was going to tell you you have to learn everything. I just think you need to learn enough so that you learn everything, so that the machine can learn everything. Now, another area that is sort of, I think, very exciting, that was nice work here by the Facebook AI research team, as well as a paper by my students at Oxford, is learning to communicate. And there's also some very nice work at DeepMind on synthetic gradients that is related to this, where we're starting to study how multiple agents can come up with discrete codes or can transmit information through very long networks. And we're learning a lot, especially how to come up with combinations of RL and backpropagation or different types of optimizations that enable us to actually learn efficiently in RNNs. So if anything, this learning to communicate is giving us a lot of insights in the design of neural networks, as well as the emergence of discrete communication. Finally, the LSTMs have been incredibly popular. I thought that was the music that I was out. I'll put that down. I'll save you the pain. So they've been incredibly popular. Tools like CTC and so on are widely used in speech. And you can just take the same net speech pipeline and you can apply it to, say, images, for example, of lips, and you can build a lip reader. So these technologies are actually quite powerful. And in fact, with a bit of invention and hard work on the part of grad students and so on, it's possible to actually come up with very nice applications that could help millions of people with hearing impairments, and also basically be able to change the way people can interact with machines in crowded environments and so on. It also poses questions about surveillance and so on, just like having cameras here poses the same question. And so we need to think wisely about the issues that we confront as scientists in AI. I'm going to end there, and thank you.
Nando, thank you. Fascinating talk. Is there a question? Questions? If not, then thank you again.
Thank you.